Hello everyone, today is a slightly different video than usual. First of all, I have been a bit busy lately, having to do some paperwork and some programming. More on that in another video. I won't waste any more time for now. Also, this video is somewhat specifically directed at other German people, and I am also German, but I will still make this video in English because it's just the most understood language, and I don't want any English speakers who stumble over this video to just sit there with Fragezeichen over their head and no idea what's going on. So today's video will be a response and analysis to some German YouTubers' first attempt at aviation. I'll keep this short for those who already know, but a short introduction for those who don't know yet. There is an event called the Red Bull Flugtag or Red Bull Flight Day, which, as Wikipedia describes it, is an advertisement event where competitors, quote-unquote, though translated, plunge themselves into the water in self-built, in quotes, flying machines. So it's a tiny bit off topic for me since it's not the most advanced or professional rocket science ever, but it's all just for fun, and sometimes some actually skilled teams actually do get quite a distance. They basically jump off a ramp in a muscle-powered or unpowered, uncontrolled glider and glide a few meters down into the water and see how far they can get. We have, by the way, used this event as an example in university before, though not for an actual technological topic, but actually in a course about English in science and technology, where we've just used it as practice material for talking about it in English, irony going full circle. Now the reason I'm making a video about this is because some other German YouTubers are competing in it this year, and they too are a little bit off topic for this channel maybe. Usually if I recommend someone, it's also someone who talks about science and spaceflight or astronomy. In this case, they're just some slightly weird German comedian slash let's player group called FliegSmiet, but I like them. I've been watching them for a very long time, and so when they got the chance to get together with another German YouTuber called Nerdy Timber, who makes big things out of wood basically, and two other German YouTubers to build a quote-unquote flying machine for this advertisement event, I thought I'd take that as an opportunity to practice some aerodynamics, explain some basic flight dynamics and aerodynamics on a somewhat entertaining example, and of course give them some final tips for how to get further. So first of all, the very basics, though I already have to clear something up that is sometimes a bit confusing and a bit argued over. But what is aerodynamics and what is flight dynamics? This is sometimes a bit confused, and you often see articles or videos called The Basics of Aerodynamics that have absolutely nothing to do with aerodynamics at all and only flight dynamics. So let's give a quick overview over these fields and my methods here. So first of all, aerodynamics. Aerodynamics is purely the study of air or sometimes other gases flowing around a geometry. Aerodynamics does not care how heavy your flying machine is, where its center of mass is, or what you're planning to do with it. According to aerodynamics, your flying machine might as well be a hollow surface, since aerodynamics is only the study of how air streams around your flying machine or any other object under certain circumstances. So you have your geometry, your size, your outer surface, which might be rough or smooth. You have air approaching it at a certain speed, at a certain angle, with a certain temperature, and maybe the surfaces have a temperature too. And you might have an engine, a propeller, a turbojet, or a rotor or something, and the air streams around that, and you study how the air streams around that, how the air interacts with the surface and with other air, and changes pressure, and goes into turbulence, and so on. And this can be simulated with quite a bit of detail, though it's actually not an exact science yet. The thing is, we do understand how it acts on a large scale, and we do understand how it acts on a very, very tiny scale. We have a very rough idea of how air molecules or atoms in air interact, but those are so many that it basically comes down to statistics, and how air actually acts in a larger quantity is somewhat experimental, and you have to get experimental values which you can then add into a numerical simulation. Nonetheless, with enough detail, you can get a somewhat accurate idea of how air reacts if it streams onto a certain geometry at a certain angle and speed, how much pressure builds up on which surface, and what kinds of forces then act on the flying machine. So you get a rough graph or table or list of numbers for different speeds and different angles of attack and side slip and rotation and so on, and you get a list of forces acting on each surface of the flying machine, which you can work on and extrapolate on. Flight dynamics goes the next step, and flight dynamics no longer really cares about the specific detailed interactions of air. It just takes these tables that aerodynamics essentially outputs, and that actually then takes the center of mass of your flying machine, the weight of your flying machine, the thrust of your engines, and so on, and looks how do the forces acting on the surfaces, how do these aerodynamic forces change the path of the flying machine, change the speed of the flying machine, how do they create torque and turn the flying machine, which then in turn changes the aerodynamics, changes which numbers you basically look up in these tables. And this is where, for example, terms like aerodynamically stable or unstable come from, whereas a stable means that if you deviate from a straight path, that will result in forces that basically turn you back onto that straight path, whereas unstable means if you slightly deviate from a straight path, that will result in forces which turn you further in the same direction and make you further deviate from that straight path, making you unstable. Basically, as soon as you turn slightly off your path, you instantly backflip against your will, whereas stable means you are turned back forward. Of course, nowadays with modern computers, that is modern supercomputers of the kind I don't have, the kind that cost several $1,000,000, you can do some much more complicated simulations where all these fields interact, structural analysis, flight dynamics, aerodynamics, and then you get into aeroelastics where you look at the feedback loops of how aerodynamics creates a force on a wing, that force bends the wing, that changes the geometry of the wing, that again changes the aerodynamics, that changes the force on the wing, that changes how the wing bends, and so on, and that gets you a feedback loop which you can analyze, and you can do that all in detail using numerics if you have the computing power. But for now I've just started out with doing a basic aerodynamic simulation. I've used the 3D model they uploaded, the measurements and sizes from that 3D model, as well as the video of the flying machine that we already have, to make a rough model in SolidWorks. I then added a human dummy figurine, which is actually something I'm practicing for the first time, since until now I have done quite a few aerodynamic simulations, but usually on either unmanned drones or large aircraft, or at least something with an enclosed cockpit. This is the first time I'm actually using a human dummy to represent an open cockpit glider, or a glider where the human is basically just lying on top. So the flying machine looks like a giant PlayStation controller, which is basically their logo, their symbol, and it's not aerodynamically perfect, but that's not the point. It's just for fun. It has to look this way, and it actually turns out surprisingly well. So you take the outer shape, the outer surface of the 3D model, and you take the space around it and separate it up into tiny cubes or cells. At varying levels of detail, these cells interact with each other, and then you basically go to sleep while your computer works, and when you wake up it has finished up some colorful images of how pressure and speed and turbulence is distributed around the machine. With some understanding of basic physics or a bit of experience, you can of course tell some interesting things from these images, like where the average forces are applying, if that thing would be stable or unstable, if there are any critical errors in the aerodynamics. In this case, the only really big issue is that it's slightly stall sensitive, at least without the pilot. I did a simplified simulation without the pilot at first, and that turned out very sensitive to stall because of these bumps in the front of the machine and the straight line connecting them, which basically catches in air and turns it into a turbulence above the center of the machine. Now with the pilot that's actually a bit less of an issue, since the pilot causes some turbulence anyway, but relatively harmless ones that basically overact these turbulences caused by the straight edge at the front. I have also uploaded some detailed long videos of the whole analysis of all the colorful images of pressure and airspeed, so you can look at all the details. They're relatively long, no commentary, relatively boring, but if you are interested in the actual details, you can check them out for a moment. Then I looked at these images and actually analyzed them and got the actual forces acting on the machine, the drag, the lift, where these forces on average act on the machine, and that is where we go into flight dynamics, which is basically Newtonian mechanics. We can draw up a very simplified sketch here. We have the rough outline of the machine, the center of gravity, and that's where we get a little bit of an issue because the pilot is resting on top. And writing with the guy who built the machine, I read that it's roughly 27 kilograms heavy. I'll estimate the pilot at some 80 kilograms or something roughly around that area. So the whole thing is going to be a bit over 100 kilograms, and the flying machine itself is going to contribute the lesser part of that. So the center of mass is going to be closer to the pilot's center of mass than the machine's own center of mass, which means since the pilot is resting on top, that the center of mass is going to be above the flying machine itself, which is a bit of an issue because while humans do cause some drag, the machine is much bigger. It has large wings which are somewhat aerodynamic and don't cause too much drag, but still more than the human, and so the force of drag, the force pulling you backwards as you move forward, is attacking below the center of mass, so the whole thing gets turned around its center of mass basically. So the lower side gets moved backwards, the upper side gets moved forwards, which basically means the nose moves down and you nosedive. However, that's actually not that big an issue, since the whole thing is actually not going too fast anyway, and the drag itself, the parasitic drag as we call it, the drag actually caused by the edges in front and the roughness of your surface and so on, is relatively low, and the strongest forces will be lift. So the main part of drag too would be induced drag, that is the drag caused by your own lift and the angle of attack of your wings, where your wings are angled upwards, so your lift is not going straight up but slightly angled, and thus it also pulls you backwards a bit, and that induces a drag called induced drag, which is a direct side effect of lift and thus also attacks in an angle, basically upwards. So the forces actually pulling the machine straight backwards are actually relatively small. They also attack with a relatively small lever, since the whole thing is rather flat. After all, the pilot is not sitting but lying on top of it. And the forces that mostly dominate how the machine will turn and rotate and flip back or forth will be lift itself, and the center of lift, or where the lift attacks under the wing on average, is actually somewhat well lined up with the center of mass, so it shouldn't turn or spin too much. Also, of course, jumping down 6 meters, it won't be the longest flight ever, so the machine might simply not have quite the time to actually start rotating, rather just staying close to its original flat position, so stability and such aren't actually that relevant here. As far as control goes, it will basically be like balancing on a huge gymnastics ball. You can, as the pilot, you can shift your weight forwards or backwards, and if you slightly shift your weight to the tail end of the machine, you will start pulling your nose up, whereas shifting your weight forward to the nose of the machine will basically initiate a nosedive. So you can try to keep the whole thing somewhat controlled by moving your hands back and forth, but that will hardly be needed over the short time that it will fly. I have actually gone for a trajectory simulation where I've used actually Excel, since it's not that complicated, it doesn't really take anything more advanced. So this is again just a basic recursive simulation. You start with your starting position and your starting speed, and then you calculate from that position and speed the forces acting on the machine, extrapolating that from the data points you got from your aerodynamic simulation. You calculate how fast the machine will turn and how that will change the angle of attack and the lift. And you do that basically in 1/100th of a second steps, and then you enter the next speed, which is a result of the acceleration, and the next position, which is a result of the last position and the speed. Of course, in Excel you can just pull that down and it does that automatically. So I have roughly calculated for you what your flight trajectory might actually look like, and how far you can get depending on how fast you start, which is very critical. I've plotted the flight trajectory for different speeds, and I've also plotted the maximum distance you could reach as a function of the speed you start at. The machine, as far as I've understood, will be started by pedaling on bikes and pushing it forward. Now, I'm an aerospace expert, not a human athletics expert, so I don't really know how fast exactly that might get. It is a rather special situation too. But as a good guess, I've given roughly 10 meters per second, which is also where you basically start to fly, where your aerodynamics start having a significant impact on how far you go, and you actually go significantly further than just a concrete boulder. Now 1 meter of second, of course, is 3.6 kilometers an hour, so 10 meters per second are 36 kilometers an hour, or 24 miles per hour, or roughly 20 knots. And here I've plotted the range you could reach for a given speed compared to a block of cement just tossed at that speed without wings. And you can see in the beginning at some 6 or 7 meters per second that is a very similar range, and as you approach 10 meters or 12 meters per second you can get a lot faster than a boulder tossed at the same speed. And of course I'm hoping for you that you can go fast and crack the 20 meters, maybe even the 30 meters if you can go really fast. As you can see, it would take you roughly 15 meters per second or 54 kilometers an hour to beat the world record in this type of jump. So I'd say go for it and good luck, and to everyone else. And next video I might be getting around to telling you all what I've been working on for a while. I hope you enjoyed this little over-analysis of your just for fun flying machine, and as always, thanks for watching.